Starting with Chapter 8, we're going to cover internal flow. Internal flow through pipes, elbows, tees, valves, etc., as in this oil refinery, are found in nearly every industry. So, of course, internal flows are in every industry, right? You have working fluids, you have water, you have air, gases, things like that. In vehicles, in large equipment and small equipments, even in you have internal flow of the blood going through your body. Here's our objectives. So just to introduce it, liquid or gas flow through pipes or ducts is commonly used in heating and cooling applications in fluid distribution networks. So basically, if you need to get a working fluid, and in this course we're talking about liquids and gases, you are going to distribute that fluid through a network, getting from point A to point B. And you do that through going through pipes or ducts. So you can see a circular pipe down here, just a traditional circular pipe. And then what we find is a rectangular duct. Obviously, you can have a plethora of different shapes, right, of any of these. And then the fluid in such applications is usually forced to flow by a fan or a pump through a flow section. So usually it has some sort of force to create that flow of the fluid. We pay particular attention to friction, which is directly related to the pressure drop and heat loss during flow through pipes and ducts. So if you have, 100 degrees Celsius here flowing through this pipe, of course this is a short pipe, so it's going to be negligible difference when it comes out the other side. We will still have a pressure drop, but not as much as if it was a very long distance that it was traveling. So because friction here and just heat loss in general, heat being absorbed, right, you're going to have less than 100 degrees Celsius here. So we try to take into account all of those so that if you know what you need at the end, you can, if you know that you need 80 degrees Celsius, well then pumping it in at 100 degrees Celsius may be sufficient. The pressure drop is used to determine the pumping power requirement, right, what we need. Theoretical solutions are obtained only for a few simple cases, such as fully developed laminar flow in a circular pipe. Therefore, we must rely on experimental results, right? So therefore, we must do some trial and error and empirical relations for most fluid problems rather than closed form analytical solutions. And that's because the things that you will run into, the friction losses, the just absorption from the atmosphere, the impact from the surroundings, things like that, it's really hard to incorporate all of those in an analytical solution. And a lot of these things can be experimented on in small doses, right? A small pipe with a small amount of working fluid. Here's some formulas here. We've got a mass rate, okay? Average velocity here for incompressible flow in a circular pipe with a radius, okay? So just some formulas here. And again, the value of the average velocity at some streamwise cross-section is determined from the requirement that the conservation of mass principle be satisfied. So here we talked a little bit about what a laminar and turbulent flow is. So laminar here is just the steady flow. It's the things that look uniform, pretty straight and narrow or smooth, and then when we start getting into flows that look disorganized, much more entropy, that's when we start getting into turbulent flow. So laminar, smooth streamlines and highly ordered motion. Turbulent is velocity fluctuations and highly disordered motion. And then transition is the flow that fluctuates between laminar and turbulent. So you could say that this right here is that transition. So it's just where you transition from. Most flow encountered in practice are turbulent, and that's because things, especially when you're talking about liquids and gases, they want to spread out, right? Gases way more than liquids, because liquids have that that need to, kind of stay together, that molecular draw to each molecule. The gases really want to spread out, but by and large, fluids and gases, they just want to fill the space that they can occupy. And so you can see here, if you're injecting a dye trace here, and you have a flow that looks like this, well, then that's going to be a laminar flow. It's going to be very steady, right? And then if you have something that's kind of all over the place, then you've got a turbulent flow. So here's the Reynolds number. The transition from laminar to turbulent flow depends on the geometry, surface roughness, flow velocity, surface temperature, and type of fluid. So it depends on a lot of things, right? The transition point from the laminar to turbulent is going to depend on the parameters at which it's set and the environment in which it is operating in. The flow regimen depends mainly on the ratio of inertia forces and viscous forces, which is the Reynolds number. Right. So taking from that, when you have the ratio that becomes a large Reynolds number, it's because the viscous forces are not large enough to counteract these inertial forces, which result in a turbulent flow. When you have small or moderate Reynolds numbers, those viscous forces are large enough to balance or counteract these inertial forces, and therefore you have something more steady, more streamlined, more inline. You have a laminar flow. You also have a critical number. This critical number, denoted by RE sub CR, is the number at which it's going to alert you when you are transitioning from laminar to turbulent. It is dependent on the geometry, the environmental factors, and it is unique to each one of those. Here are the formulas for each geometric profile of what it's working through. Here is a range that you can see for a circular pipe. So you have 23, less than or greater to, and this is RE for transitional, it's 4,000. And so you would have turbulent over here and laminar over here. Oh, it's down here. We have the velocity boundary layer. It's the effects where the fluid viscosity are felt, those shearing forces caused by that. The boundary layer is when those viscous effects and the velocity changes are significant. And then the irrotational flow region is when the frictional effects are negligible, because if you have something that's irrotational, you're not going to have a lot of friction happening. So those are going to be negligible and the velocity remains basically the same. Here you have the entrance region. That's at which the boundary layer merges at the center line. It's the pipe inlet. The entry length is the measurement of that region. Developing flow is the flow in the entrance region because you are developing. The fully developed region is when those velocity profiles remain unchanged. And then when you get to fully developed, that's when you have that, not only that velocity profile unchanged, but as well as a normalized temperature. You can see that here. So you see we still have some dropping, nothing's starting to level off, but we haven't gotten it there. And then about here is when we really do get some consistent lineage. So we've got a fully developed region, and then you've got an entrance region, and you've got the length of that as well. Here you have the hydrodynamic entry length for laminar flow formula, the turbulent flow, and then turbulent and approximation. And that's the, both all of those are the lengths. Oh, just a note here. You can start mapping it about 2%, right? So the entry length is taken to be the distance from the pipe entrance where the wall shear stress reaches within about 2% of the fully developed. So that's when you can start and plot the start of that length. Here we have some formulas just being derived from here. But this is to let you know what we are working with: steady, laminar, incompressible, constant properties, fully developed, And then the things that you can derive from there, right? So no motion in the radial direction. You've got normal to the pipe is everywhere 0 for the velocity. You've got no acceleration since the flow is steady, fully developed, ET. Okay? And then for here, you have formulas driving down for boundary conditions, average velocity, velocity profile, and max velocity at the center line. You have pressure drops and head losses. So again, more formulas. You've got changes in pressures 1 to 2, things like that. Pressure loss, circular, pipe, laminar, head loss. In laminar flow, the friction factor is a function of the Reynolds numbers only and is independent of the roughness of the pipe surface. So we just taken to this friction factor being a function of the Reynolds number. A head loss represents the additional height that the fluid needs to be raised by a pump in order to overcome the frictional losses in a pipe. So what you would need additional. The relation for pressure loss and head loss is one of the most general relations in fluid mechanics and is valid for laminar or turbulent flows, circular or non-circular pipes, and pipes with smooth or rough surfaces, so it's widely used. We have some more formulas given here. So we've got work rate of a pump length, horizontal pump, velocity rate, and then Poiseuille's law. So for a specified flow rate, the pressure drop and thus the required pumping power is proportional to the length of the pipe and the viscosity of the fluid, but it is inversely proportional to the fourth power of the diameter of the pipe. And the pumping power requirement for laminar flow piping system can be reduced by a factor of 16 by doubling the pipe diameter. So the pressure drop equals the pressure drop L in the case of the horizontal pump, but that is not the case for inclined pumps or pumps with variable cross-sectional areas. This can be demonstrated by writing the energy equation for steady, incompressible, one-dimensional flow in terms of head here. And this is just giving you information about how we derive these formulas. The effect of gravity on velocity and flow rate in laminar flows. So here, again, just more deriving of formulas. And then the relations between fully developed laminar flow through horizontal pipes can also be used for inclined pipes by replacing the change in P with change in P less rho GL sine theta. And this is giving you this information. And then for uphill and back downhill, you can also see horizontal and inclined. And again, this is just supplying the formulas and giving background information. This is friction factors being developed laminar flow in pipes of various cross sections, as well as the tube geometry associated with each. So you've got circular, rectangular, ellipse, and isosceles triangle, and then the theta for that, AB, and then none here because it's just the geometry, but you get this frictional factor here associated with each, which is nice. So you get this for that area, this for that area, and then the theta as well. And that's for fully developed laminar flow in pipes. Turbulent flow in pipes, it's a complex mechanism dominated by fluctuations, and it's still not fully understood. And I do believe it's because it's just so chaotic, right? So before turbulence, we have a lot of just very steady, very uniform flows. And then after turbulence, it's very, very chaotic. And we have a measurement for that in thermodynamics, and it's entropy. It's the disorder of things. And that is very difficult to wrap your head around in some ways and to calculate and to grasp. So here you see water exiting this flow, and that's going to be that laminar at a low flow rate. B is turbulent flow at a high flow rate, so lots of disorder going on. And then C is the same as B, but with a short shutter exposure to capture the individuals. So C is the exact same flow conditions as B, just taken with different shutter exposures so that we can see the chaos more clearly. Here's additional formulas as well. Fluctuations of velocity component U with time at a specified location in turbulent flow. The laminar component accounts for the friction layers between layers in the flow direction. So this is for the friction between those layers. And then the turbulent component accounts for the friction between the fluctuating fluid particles in the fluid body. So you get both components to account for the friction depending on the flow. And then you see you have total is equal to the laminar and the turbulent flow. Turbulent shear stress. So here, turbulent shear stress in this formula as well. And then you can have terms such as these and these are called Reynolds stressors or turbulent stressors. We've got eddy viscosity or turbulent viscosity accounts for the momentum transport by turbulent eddies. You've got total shear stress. And then you've got kinematic eddy viscosity or kinematic turbulent viscosity, just depending on which flow you have. You've got additional formulas here and the velocity gradients at the wall, and thus the wall shear stress are much larger for turbulent flows than that of laminar flows, even though the turbulent boundary layer is thicker than the laminar for one of the same value of the free stream velocity. So here are turbulent velocity profiles. A very thin layer next to the wall where viscous effects are dominant is the viscous or laminar or linear or wall sublayer. The velocity profile in this layer is very nearly linear and the flow is streamlined. Next to the viscous sublayer is the buffer layer. It's which turbulent effects are becoming significant, but the flow is still dominated by the viscous effects. Right, it's very large viscous there. Above the buffer layer is the overlap or transition layer, which is also called the inertial sublayer, in which the turbulent effects are much more significant, but still not dominant. So it's starting to catch up. Above that is the outer or turbulent layer in the remaining part of the flow, which determinate effects dominate over the molecular diffusion, viscous effects. So this is when the viscous is no longer able to counteract. Here we have additional formulas. This is where we really start calculating, so these will make more sense in the calculating video. I'm just going to go through. We've got viscous sublayers, layer of the wall, thickness of the viscous sublayers, viscous length that's used to non-dimensionalize the distance y from the surface, non-dimensionalized variables, and then normalized law of the wall. The logarithmic law here, and then the overlap. You can see this viscous sublayer, the buffer, this overlap, and then finally reaching that turbulent. For the outer turbulent layer, we do have a velocity defect law. And the deviation of the velocity from the centerline value, U max less U, is called the velocity defect. We do have a power law velocity profile. And the value N equals 7 generally approximates many flows in practice, giving rise to the term 1/7 power law velocity profile. power law velocity profiles for fully developed turbulent flow in a pipe for different exponents and its comparison with the laminar velocity profile. So you can see here, you can see n is equal to 6, n is equal to 8, n is equal to 10. But you get much more steady when you get n equal to 7. And so generally, right? And that's where you get 1/7 power law velocity profile. So we have Moody chart and its associated equations. So we have the Colebrook equation, and that's for smooth and rough pipes. And here that is. And the friction factor in fully developed turbulent pipe flow depends on the Reynolds number and the relative roughness. Here's the roughness values, the equivalent roughness values for new commercial pipes, right? Because we know that it's dependent on, we've got feet, millimeters, roughness, wood, rubber, all that. And then over here as well, relative roughness and friction factor. Here you can see the Moody chart. And so we have laminar flow, we have laminar, traditional, and turbulent flows, we have smooth pipes. Lots of things are fully developed turbulent flows. So lots of numbers on here, and it's plotted for the Darcy frictional factor versus Reynolds numbers, as well as the relative roughness on the right side. So some of the observations from the Moody chart is for laminar flow, the friction factor decreases with increasing Reynolds number, and it is independent of surface roughness. So you can see that here, right? Darcy friction factor drastically decreasing while we're increasing in the Reynolds number, right? And then here, the friction factor is a minimum for smooth pipe and increases with roughness. And let's go back and look at that. So you see smooth pipes, right? We do have a minimum, but it does increase. The Colebrook equation in this case reduces the Prandtl equation. And then next we have a transition region. Whoops. That's here in the shaded region. This is transitional. And at small relative roughness, the friction factor increases in the transition region and approaches the value for smooth pipes. So you can see that here. It's small, but it's starting to approach and level off for this roughness right here for smooth pipes. And then a very large Reynolds number, which is on the right side. You have that frictional factor and corresponds with the relative roughness. And so you see that because Reynolds is over here. So as we're increasing and getting these large Reynolds numbers, these are starting to level off, right? And corresponding with the roughness. And again, at very large Reynolds numbers, the frictional factor curves on the Moody chart at nearly horizontal, and thus the friction factors are independent of the Reynolds number. Standard sizes for Schedule 40 steel pipes. It's by and large used in a lot of industries. And in calculations, we should make sure that we use the actual internal diameter of the pipe, which may be different than the nominal diameter. So you want to make sure that you're using that because that's what's experiencing the flow, right? So you've got different types of fluid flow problems. And so you've got pressure drop or head loss, you've got flow rate, and you've got pipe diameter. And here you can see, it gives you problem 1, which would be that head loss, what you're given, and what you need to find. So to avoid tedious iterations of head loss, flow rate, and diameter calculations, these explicit relations are to accurate within 2% of the Moody chart, and you can use this. So these are ones that you can use that can give you a really close approximation for when you're talking about head loss, when you're talking about velocity changes in diameter. So you have the explicit Holland equation, and the results obtained from this relation are within 2% of those obtained from the Colebrook equation. And here's the explicit Churchill equation, which was generated by Churchill in 1997, that not only explicit but is also useful for any Reynolds and any roughness, even for laminar flow, and even in the fuzzy transitional period within the laminar and turbulent flow. And you can see that the difference here is less than 1%. So minor losses in a fluid in a typical piping system passes through fittings, valves, bends, lots of things, inlets, outlets, elbows, tees, lots of things, connections, things like that. These components interrupt the smooth flow and cause additional losses. Flow separation, mixing they induce, friction, heat loss, leaks, all kinds of things. In a typical system with long pipes, these losses are minor compared to the total head loss in the pipes, which are the major losses, and they are called minor losses. Minor losses are usually expressed in terms of a loss coefficient, which is KL, and here's the formula here. And then you do have head loss due to component. So here you have when the inlet diameter equals outlet diameter, the loss coefficient of the component can also be determined by measuring the pressure loss across a component and dividing it by the dynamic pressure. So here you have minor loss again, and then minor losses are also expressed in terms of the equivalent length here. Total head loss, which is just a general equation here, and then total head loss when D is constant. And then these are loss coefficients for various pipe components for turbulent flow in relation for these. So you can see pipe inlet, pipe exit, sharp-edged KL, here well-rounded. So all of these differences that can be found all right here. And you can see that the flows are differing, whether they're going in or out. So sudden expansion and contraction. So we have one for sudden expansion as well. So you can see it's expanding, right? And then sudden contraction, you can think of this as a diffuser of some sorts or a nozzle of some sorts, this flow, right? Okay, and then you do have gradual and contraction based. So you have this here. Bends here, got branches, we've got a 180 return bend, you've got a T, really an upside down T, right? And then a threaded union, so this is conjoined and then it's threaded here. And then, oh, whoops, down here at the bottom, we have some valves as well. So these are just KLs for each of them, and it gives you each type, right? You've got a flanged or a threaded. So here you have sudden expansion here, and you can see that as well. Graphical representation of flow contraction and the associated head loss at a sharp edge of the pipe inlet. And then this is the effect of rounding of a pipe inlet on the loss of the coefficient. So right here, this is what you're looking at. This point right here, this is what's happening. Here's some schematics to help illustrate submerged outlet, you've got some mixing going on, you've got some entrained ambient fluid. You've got flow here, you've got some streamlines. Okay? And so all the kinetic energy of this flow is lost, turned into thermal energy through friction as the jet decelerates and mixes with ambient fluid downstream of a submerged outlet. And the loss during changes of direction can be minimized by making the turn easy on the fluid, by using circular arcs instead of sharp turns. So you can just think the flow is going to be, if you have a particle up here, right, and it bumps here, you can kind of think of it like a like ping pong, right? Versus if it's over here, you know, and it goes through, it hits here, and then it might come all over before it starts going down, right? And it'll happen really quickly, but you can kind of ease it in versus just a sharp turn. Here we've got a globe valve. The large head loss in a partially closed valve is due to the irreversible deceleration flow separation. And that's because it's interrupting it. The mixing of high velocity fluid coming from the narrow valve passage. And then B, so it's illustrated here in A, and then B, the head loss through a fully open ball valve, on the other hand, is quite small. And that's because it just kind of creates just another small pipe for it to flow through instead of something being interrupted here with this construction. So here's some piping networks and pump selection. So this is when you can get into which pump would be right for your setup, for your design, the piping network to go along with that, right? So a lot of the times you see pipes in parallels, right? So 4 pipes in parallels, the head loss is the same in each pipe. It's the same here, same here. And the total flow rate is the sum of the flow rates in the individual pipes. For pipes in the series, the flow rate is the same for each pipe. And the total head loss is the sum of all the head losses in the individual pieces. So relative flow rates in parallel pipes are established from the requirement that the head loss in each pipe be the same. And so here you can see that head loss in 1 is equal to head loss in 2, and therefore given these, as well as here. And so the flow rate in each one of the parallel branches is proportional to its diameter to the power 5/2 and is inversely proportional to the square root of its length and friction factor. So when you're analyzing piping networks, it's based on 2 simple principles. Conservation of mass throughout the system must be satisfied, right? Because what is the point of having a piping network if you can't conserve the mass, if you can't get what you put in to get to the end, right? So conservation of mass throughout the system must be satisfied. This is done by requiring the total flow into a junction to be equal to the total flow of the junction for all the junctions in the system. Of course, you need a piping network that doesn't have an obscene amount of leaks, right? Hopefully no leaks. And then pressure drop, or thus head loss between 2 junctions, must be the same for all paths between 2 junctions. This is because pressure in a point function, and it cannot have 2 valves at the specified point. In practice, this rule is used by requiring that the algebraic sum of the head losses in a loop for all loops equals 0. So you can think of it as a balancing act. Every time you set it equal to 0, it's because you're balancing something. So piping systems with pumps and turbines, we have here steady flow energy equation. When a pump moves a fluid from one reservoir to another, the useful pump head requirement is equal to the elevation difference. So we have an elevation difference between the 2 reservoirs plus the head loss. Here, so you see the elevation difference plus the head loss. Here you've got the work rate of a pump and the shaft work associated, and then the elect as well. And the efficiency of the pump-motor combination is the product of the pump and the motor efficiencies. So here you have a characteristic pump curves for centrifugal pumps and the system curve for piping systems and the operating point. And so you can see here the pump exit is closed to produce maximum head, shutoff head. And then you can see it decreasing as we've got that flow rate. And then no pipe is attached to the pump, so no load to maximize the flow rate. And then here you have the efficiency of the pump going up and then down. We have free delivery. We have, this should be the operating point because we have a system curve over here, and the point at which the system curve meets the solid line is going to be that operating point, right? And then you have that supply curve as well. And this is all mapped on that pump efficiency as well. So even that operating point, that pump efficiency is going to be at, what would that be, maybe 49%? Close. So flow rate of cold water through a shower may be affected significantly by flushing a nearby toilet. Haven't we all experienced that? Flow rate and velocity measurement. Here you can see she's timing, she's got her nozzle, she's got her garden hose, which is her pipe, and the bucket and the stream here. And so a major application area of fluid mechanics is the determination of the flow rate of fluids. And numerous devices have been developed over the years for flow metering, right? Flow meters range widely in their level of sophistication, size, cost, accuracy, versatility, capacity, pressure drop, and the operating principle, right? So just depending on what you need and what your budget and what your parameters are. We give an overview of the meters commonly used to measure the flow rate of liquids and gases flowing through the pipes or ducts, but we do limit our consideration to incompressible flows. You see that as a theme throughout this class. Measuring the flow rate is usually done by measuring flow velocity, and many flow meters and simple velocimeters used for the purpose of metering flow. A primitive and fairly accurate way to measure the flow rate of water through a garden hose involves collecting water in a bucket and recording the collection time. So you have pitot probes or pitot tubes or pitot-static probes. They're widely used for flow speed measurement. A pitot probe is just a tube with a pressure tap at the stagnation point that measures the stagnation pressure, while a pitot-static probe has both a stagnation pressure tap and several circumferential static pressure taps, and it measures both stagnation and static pressures. So this pitot probe is just inclusive of the stagnation pressure, and then the pitot-static includes the static as well as the stagnation pressure. Here you can see the pitot-static probe here, and you can see that inclusive of the static pressure as well as the stagnation pressure in the flow. You've got the pitot formula. And then here, measuring flow velocity with the pitot-static probe. A manometer may be used in place of the differential pressure transducer. And then this is a close-up of a pitot-static probe showing the stagnation pressure hole and 2 of the 5 static circumferential pressure holes. Obstruction, flow meters, orifice, venturi, and nozzle meters. So flow meters based on this principle are called obstruction flow meters and are widely used to measure flow rates of gases and liquids. You have a mass balance for that, a Bernoulli equation, and then the obstruction with no holes. And then you see this flow through a constriction pipe. Here, you can see that the flow is constricted. The losses can be accounted for by incorporating a correction factor called the discharge coefficient, denoted here by C subscript D, whose value is less than 1, and it is determined experimentally. Here's the obstruction flow meters. The value of CD, that discharge coefficient, depends on both B and the Reynolds number, and the charts and the curve fit correlations for the discharge coefficient, are available for various types of obstruction meters. So you see the orifice meters, the nozzle meters, and you see here for E and the Reynolds number. For flows with high Reynolds number, RE in excess of 30,000, the values of the coefficient discharge can be taken to be 0.96 for flow nozzles and 0.61 for orifices. So that's where it tends to level off here and here. So it tends to become pretty consistent in excess of 30K. So you see here an orifice meter. Okay. And then you see a flow nozzle and then the Venturi meter. Orifice meter and schematic showing its built-in pressure transducer and digital readout. Okay. And so this just shows, you see the flow is going this way. You've got one side coming in here, another lace through here to experience that flow. And then you've got the reader here, which makes it very convenient. The variation of pressure along the flow section with an orifice meter, as measured by the piezometer tubes, the lost pressure and the pressure recovery are shown. So you have that orifice meter here, and then you have this pressure drop across the orifice, and then you've got right here, it's the bottom of the drop, and then when we start coming up and leveling off, this is what we were able to recover. And then this is what was overall lost. So positive displacement flow meters, the total amount of mass or volume of a fluid that passes through the cross-section of a pipe over a certain period of time, is measured by positive displacement flow meters. There are numerous types of displacement meters, and they are based on continuous filling and discharging of the measuring chamber. They operate by trapping a certain amount of incoming fluid, displacing it to the discharge side of the meter, and counting the number of such discharge recharge cycles to determine the total amount of fluid displaced. So here we have a double, so two of these, the helical 3-lobe, each one of these is a lobe, impeller design. It's a positive displacement flow meter. Here we have the disc flow meter. And then we have turbine flow meters as well. So A here is an inline because here's that line, and so it's right into it. B is a cutaway, so you can see it's cut away. And then C is a handheld turbine flow meter, and it measures wind speed, measuring no flow at time. The photo was taken so that the turbine flows are visible. So you can see that the wind would spin this, and then it would measure this, but it's taken at none so that you can see the turbine flows. We have paddle wheel flow meters. So paddle wheel flow meters are low-cost alternatives to turbine flow meters. For flows where high accuracy is not really required, an approximation would be okay. You can see this paddle wheel here with a counterclockwise of flow. Variable area flow meters or rotometers. It's a simple, reliable, and inexpensive and easy to install flow meters with reasonably low pressure drop and no electrical connections. Gives direct reading of a flow rate for a wide range of liquids and gases, and it's the variable area flow meter, also called the rotometer or the float meter here. So you have it here. So you have A is an ordinary gravity-based meter, and B is a spring-opposed meter. So here, this is how it talks about work, but the flow rate is determined by simply matching the position of the float against the graduated flow scale outside the tapered transparent tube, and the float itself is either sphere or a loose-fitting piston-like cylinder. So it just goes up and down. and that's how you would read it. As fluid flows through the tapered tube, the float rises from the tube. Weight, drag force, buoyancy, force, balance, all of that. So it rises and it falls. Ultrasonic flow meters operate using sound waves in the ultrasonic range. This is beyond our hearing, typically at 1 megahertz. Ultrasonic or acoustic flow meters operate by generating sound waves with a transducer and measure the propagation of these waves through the flowing fluid. There are two basic kinds of those ultrasonic flow meters, and that's the transit time and the Doppler effect. We've heard of that, or the frequency shift of the flow meters. You can see this here. And just to note, this L is the distance between the transducers, and K is a constant. Doppler effect ultrasonic flow meters measure the average flow velocity along a sonic path. And you can see here it's transmitting from here, and then we've got reflectors, and then this is what is received in a flow direction here. Electromagnetic flow meters are full flow electromagnetic flow meters, non-intrusive device that consists of a magnetic coil that encircles the pipe. So this is something that you can use external and really not interacting at all with the contents or the working fluid inside the pipe. And here, this is how you can reduce any head loss. Insertion of the electromagnetic flow meters operates similarly, but the magnetic field is confined within a flow channel at the tip of the rod and is inserted into the flow. So this is if you do insert it. So A here is a full flow electromagnetic flow meter, and B is one that is inserted. Vortex flow meters. The flow can be determined by generating vortices in the flow by placing an obstruction. So you have that body. And then you get these vortexes here. And then this transmits the data, and then this receives the data. The Stroll number, defined as ST equals FD over V, where F is the vortex shredding frequency, D is the characteristic diameter or width of the obstruction, and V is the velocity of the flow impinging on the obstruction. It also remains constant in this case, provided that the flow velocity is high enough. Then we have thermal anemometers, and then that can either be hot wire or hot film. A thermal anemometer is called a hot wire anemometer if the sensing element is a wire, and a hot film anemometer is the sensor in a thin metallic film. And here we have King's law. So first we have a schematic of the thermal anemometer system. And then below we have King's law, where E is the voltage, and the values for the constants A and B and N are calibrated for a given probe. Once the voltage is measured, this relation gives the flow velocity. So you have laser Doppler velocimeter as well. It's also called laser velocimeter or laser Doppler anemometer, LDA, and it's an optical technique to measure the flow velocity at a desired point without disturbing the flow. So this is another great option for when you do not need to impact the flow. Here are LDV equations, just things that work with that, schematics for a time average velocity profile in a turbulent pipe flow. And then you also have particle image velocimeter. It's a double pulsed laser technique used to measure the instantaneous velocity distribution in a plane by flow by photographically determining the displacement of the particles in the plane during a very short time interval. The PIV system can be used as a camera and can take a snapshot of a velocity distribution at any desired plane in the flow. And here you can see that PIV system to study a flame stabilization. Instantaneous PIV velocity vectors superimposed on a hummingbird in hover. Color scale is from low velocity, which is blue, to high velocity, which is red. And here you can see the three-dimensional PIV. So you can see those stereoscopic camera setups, the jet flows, the flows, things like that. And it's to study the mixing of the air jet with a cross-duct flow. Here we're going to briefly introduce the biofluid mechanics. We're going to focus more on the cardiovascular network because it's a very clear piping network within the human. But they do have plenty of other fluid systems. Aside from cardiovascular, you've got respiratory, lymphatic, ocular, gastrointestinal. There's many more. But really, it's just the piping networks that are transporting a fluid, whether it be liquid, gas, or both. And so here you see that cardiovascular system detailed here. And here's an artist's rendition of a 12 cc Pulsali 10 Penn State pediatric ventricular assist device with an inlet attached to the left atrium and the outlet attached to the ascending aorta. And then B is the direction of the blood through the PVAD. So here you can see it pumping in and out. And then here is a simplified version of the anatomy of a human body. So here's this red aorta. All of the little sprigs coming off. And then as well as the left common iliac and the right common iliac arteries that are split off. So here we talked about laminar and turbulent flows, the Reynolds number, and how that creates a low or a high Reynolds number. We've got entrance regions and then those entry links when it varies off into that turbulent region. The laminar flow in pipes, we've got pressure drops, head loss, effective gravity, velocity, flow rate, and laminar flow. Laminar flow in non-circular pipes, you were given a lot of numbers for those. Turbulent flow in pipes, you've got shear stress, velocity profile, Moody chart, and its associated equations and the numbers and relationships that you can draw from there. And then you've got fluid flow problems, one of those being that pressure drop, the diameter, the velocity, minor losses, piping networks, parallel pipes, serial pipes, right? Piping systems with pumps and turbines, and what to do within those setups, right? You've got flow rate and velocity measurements. So pitot and pitot-static probes when you're taking into account not just the stagnation pressure, but that static pressure as well. You've got obstruction flow meters, right? Orifice Ventura nozzle meters, positive displacement, turbine flow meters, variable, ultrasonic, electromagnetic, vortex, thermal, laser, LDV, PIV, and then just a small introduction into biofluid mechanics as well.